So, greetings students. Welcome to today's lecture. So, today's lecture will be continuation of your alternators. Okay. So, we'll be dealing with the load conditions with respect to your alternators. Okay. What based upon the different load conditions. You already know. So, in a synchronous machine, you'll be having stator as well as rotor. So, your rotor will be the stator will be given with your AC source. Okay. Whereas your rotor will be supplied with that of your DC. So the machine is introduced to normal working conditions. In the working condition, so the load might be either in star or delta. Okay. So in today's lecture, we will be dealing with your load conditions. After that, at the end, we will be dealing with the differentiation between an induction machine and your synchronous machine. So here you can see this is your field rheostat. Okay. So by wearing this field rheostat, you can vary the excitation at your rotor side. So this is your equivalent circuit of your synchronous machine. So here your rotor side is given with your DC field. Okay. So for the per phase equivalent circuit, that is for your AC side. So the equivalent circuit is this. So here the synchronous reactance include the reactance XL, that is your leakage reactance. Okay. And this is your armature resistance. So after this, you will be connecting to your load. Okay. So coming to the power flow out of a synchronous machine. So over here it will be your DC excitation, and from here you will be getting your mechanical force. Okay. So generally, what happens if you are operating it as your generator? Okay, if you are operating a synchronous machine as a generator, the flow will be outwards. Okay, the flow will be outwards. At the same time, if you are operating it as a motor, the flow will be inwards. So here the excitation voltage. So excitation voltage is here. So generally, in case of your motor, you will be calling that as a back EMF. So your excitation voltage is at the armature side. Okay, and terminal voltage is Vt. So IL is your load current. ZS is nothing but your synchronous impedance. So coming to your power flow out based upon your various load conditions. Okay. So here in general your excess, that is your synchronous impedance, will be always greater than your RA. Here you can see, so the combination of your armature leakage and your XAR is nothing but your excess. This excess will be always greater than your RA. Okay. So what happens if excess is always greater than RA? In the sense, always this resistivity will be always lower than of that of your impedance. Okay, so we could assume that you are generally considering your x, that is for your impedance value, you will be always taking only your sorry, for reactance value, you will be always only taking your impedance. Okay, so that is your excess is only consider your RA will be neglected since it is of a very small value. Okay, so here uh, generally what happens here, E will be equal to Vt plus J IL XS, okay, plus IL into RA. So this RA value will be getting 0. Okay, we are neglecting this value. So you will be getting your EMF as uh, equal to Vt plus J IL XS. Okay, so we are making this equation in your phasor format. So I already told how to draw your phasor format with respect to your second unit itself. Okay. So here this is your Vt. So your Vt will be displaced by an angle del. This is a load angle. So that is from the terminal voltage to that of the excitation voltage. The difference is given by your load angle. Okay, it is displaced by your load angle. So you can take this as your reference 0. Okay, it is displaced by your load angle. And this is your voltage drop, and this voltage drop is represented by this blue line. Okay, finally this is IA. This IA is nothing but the current flowing in your armature. So generally we are neglecting this RA, but we are considering this IA. Since RA is very negligible, so hence contributing to the flow of your IA. So moving on, power flow out of a synchronous machine. So this contributes to the continuation of the previous one. So here you can take an excitation part, that is your power is generally given by VA cos phi. This corresponds to a real power. Okay, this corresponds to a real power. So here in the diagram there's a value of H. Okay, so this contributes to the excitation. So this H is nothing but IL excess cos phi. It is this part. This part they are saying. This part they are saying this as IL excess cos phi. Actually, this would be coming as like this, not like this. It will be coming like this. So this value you have to take it as your H. Okay, this value you have to take it as your H. So you'll be getting. You are applying. This is your cos phi. So cos phi is nothing but here. So this is your cos phi. This corresponds to your cos phi. So over here, the cos phi will be correspond to over here. So this will be again coming with respect to your phi. So if this is phi means this here will be coming with respect to your phi. So this is more or less based upon your alternating angle concept. So after this, what happens that so this cos phi into IL excess will be equal to this E sin del. That is this value of your sine. So here your IL cos phi is given by will be equal to, that is your excess is brought to your denominator. Okay. And after this so here you can see this value is nothing but your E into sin del. Okay, this H value. Okay, this H value is equal to E into sin del. If you are applying your Pythagoras theorem over here, at the same time if you are applying your Pythagoras theorem over here, in the sense this J into XLS will be into cos phi. Okay, into cos phi will be equal. So these two values they are equating. You have to apply Pythagoras theorem for the triangle. Okay. So now from the two equation, that is we have already got your output power. So this is you have to substitute IL cos phi over here. So you'll be getting your output power as P out equal to E sin del XS into V. So here you can clearly see that there will be two voltage parameters. One is your E and another one is your V. So E corresponds to your excitation voltage, whereas your V corresponds to your terminal voltage. So excitation voltage will be corresponding to your field winding, which is nothing but in your rotor. Okay. So here, if you are applying, in order to get a maximum power out, so in order to get a maximum power out, if you are now talking about your generator, in the sense, if you want to get a maximum power out, your sin del value has to be 1. So if this sin del has to be 1 means, sin del tends to be 1 means your del value will be tends to 90 degree. So if you're applying sin del to be 90 degree means sin del 1. So you'll be getting the maximum power out P out as EV by X. So here E corresponds to your terminal excitation voltage, V is your terminal voltage, X is your synchronous impedance. So coming to the comparison between both your induction machine as well as synchronous machine. Here you will be considering only the motor. We are comparing with respect to your motor. So here in a synchronous motor, your construction will be complicated. Why in the sense means here for the rotor the separate excitation is needed. For the rotor, separate excitation is needed. So the construction is complex. synchronous. Whereas in case of induction motor, it is somewhat easier when compared to a synchronous motor. Okay, so these synchronous motors are not self-starting, whereas induction motors are self-starting. So you need separate self-starters. Starters are separately needed. So separate DC sources required for your rotor excitation. This is what I have said here. So here the rotor gets excited due to your induced EMF similar to that of your transformer. So here the speed is always synchronous. So this is a basic principle involved in a synchronous motor. But whereas in your induction motor, the synchronous it will be always less than that of a synchronous speed. So the speed control is not possible in a synchronous speed. But whereas in induction motor, it is possible by your armature control. And here as the load increases, the load angle increases. Load angle is nothing but del, keeping the speed constant as synchronous. Even though the load angle increases, your speed will be synchronous. Okay, but over here, as the load increases, the speed will be keeping on decreasing based upon your load. Based upon the load parameter, this gets decreasing. So by changing the excitation, the motor power factor can be changed from lagging to leading. But over here, in induction machine, it will be always a inductive load, so it will be always operating as a lagging power factor. It can be used as a synchronous condenser. So at the beginning of a synchronous machine, I have told about the synchronous condenser. Okay, whereas induction machine motors cannot be used as a synchronous condenser. So this can be used in place of your capacitor banks for your power factor improvement. So the motor is sensitive to sudden load changes, and hunting is results. So hunting also have explained. So motor is costly as you need separate excitation and all. Okay. So with this, this lecture gets completed. So thank you.